start this one. Okay, good. So I started recording this session as well. So if there are any complementary things that we happen to discuss which were not covered there, if they seem to be important thing, then we will upload it. Anyway, I think now 42 students are there, which is good. That's a very good number. Okay. So what else? Shall we go ahead now with the so in general, do you have any suggestions or do you have any problems with the video lectures as such? Any of you, if you have it, you could please let me know, so that we will try to address them. If they are, if you are fine following them, that's good. Otherwise, even if there are problems, let me know, because this is something, this is the mode in which we operate for at least few more weeks, at least this month. So it's better if there are any issues, we address them in the beginning. That would help. Okay. Yeah. So let me see the poll again now. 27 out of 42 have voted. I think those who have come joined now, they could also vote. That would give some idea. Good that out of 3 videos I have posted, nobody has watched 4 videos so far. I was expecting at least one will vote for it. Let's see. Okay, so almost 60% of you guys have watched the third one. Okay, and 30% of you guys have watched only 2 and 22% watched only 1. So I hope this is not because you had a bandwidth issue. It's time issue. If it is there, you please see. The expectation is we will be operating in the Zoom in the flipped classroom model. So unless you go through them before we have this session, it will be of not much use. It will be of little use. So I strongly recommend you, from next time onwards, you please go through it. The required videos. Yeah, I should have posted the last one bit earlier, but again it took a while. But this time onwards, I'll make sure I'll give you at least 1 day buffer before the class. The required videos are posted there. Okay, and you make sure this is more like you all know by this time. This is a flipped class model where you go through it, and this Zoom session is more for getting your doubts clarified. Okay. Yeah. Yeah, the rest of you also, please. Yeah, I'm not worried about who has gone through 1 and who has gone through 2 and 3, but it is rather to see just a general statistic. So feel free to honestly keep your numbers there, so that gives some fair idea. Okay. Yeah. And then if you have any issues also, as I mentioned, which we could address, there is a scope for addressing it. Please do let me know. Okay. Yeah. So what I will do now is I'll quickly go through the first video. That was first video lecture. That was on introduction to motion estimation. And after that, we will see if you have any questions, any doubts, or any clarifications required. We'll do that. Okay. So for that, let me share the screen here. Right. Now let me go through the PDF. Yeah, I have this PPT presentation for that's lecture 18. Okay. Right. Let me put this videos on top. Okay. Yeah, that should be fine. And let's put this in full screen mode. Okay. Fine. Right. So this first lecture is on the what it means by motion estimation, and what are its applications, and how are we going to do this estimation of the motion. So these are the things that are covered in the first video lecture. Again, as I mentioned here, this Audacity Introduction to Computer Vision is the main source, and then the rest are coming from that source itself. Okay, this is an example. Like what we see, in fact, is not the original object, the motion, but it's just the frames that have been captured at a very small intervals of time. So it appears as if it is moving. And so in other words, motion estimation is boiling down to the problem of finding out the displacements that are happening from the pixels in one image to the next image. Right. So you have sequence of frames that have been captured over time, and now each pixel here, where is its best match in the subsequent frame. That's what you are going to find out in the motion estimation. I think this is obstructing the title. So let me see if I could keep it here. That's better, I think. Okay. So then we started looking at some of the applications. One application is, for example, the background. Yeah, I think if I could move it down, let me see if I could get rid of this. Okay, that's better. So we were looking at different applications of this. One application you could think of is background subtraction. This again, for example, this video is recorded and the wall, I don't want to make you see the wall. Maybe it is dirty, or I don't want to make it, and I want to put it with some pleasant thing. Okay. So what you could do is you need to figure out what is the object, what is it that is moving here, what is it that is static here. So once you do the motion estimation, that will also tell you what is it that is moving here. Okay, so that if you consider as the object and the rest as background, then you could replace that background with whatever fancy stuff you would like to do. Okay, this is background subtraction, and then you could think of all virtual reality, augmented reality, and other things as well here. Okay, this is another fancy application you could think of. In a video captured, sometimes what could happen is there might be a sudden change in the camera position itself, or it might be moving to a different shot. For example, imagine it this way. I made this video lecture, and then you want to, one project that earlier batch student was doing is to extract the key slides of this presentation. Like they could, for example, that is what YouTube could give you as what is the slide that you want to keep it, or you just want to make a PPT out of your out of the whole presentation. So then what would you like to do? You would like to see here what is it that there is a sudden change is there. So even if you do the motion estimation here, you could come up with a nice project where you would extract all the slides from a given PPT as well. That's one application you could think of. Okay, or else in movies also, when they are making it, where is it scene is suddenly changing, that's what they refer to as shot boundaries. So to get that shot boundaries also, this can be used. Okay, and now we assume that you are keeping track of the traffic with the cameras, surveillance cameras. Then different things would be moving in different directions. So you want to get the motion. So which are how many objects are there, in which direction they are moving. So that motion segmentation also would help you that which is the, so even there is an overlap with that object with the background, you could be able to distinguish them quite well, particularly because that is moving with respect to the background. Right, this is another application where you would see an example here where the background and foreground have a lot of similarities in terms of intensity. So if you just use any simple segmentation approaches, it becomes hard. On the contrary, you could make use of the motion. If it is a video that has been captured, you could see then which are the objects, or which are the pixels that are moving here, or pixels where there is a movement, in other words. Okay, and then that would help you to segment your objects of interest, right? And then this, for example, you are moving camera, that can be done. And even if you're not, while moving camera, assume that there is a motion of the planes also. Still, you could figure out the motion, and you could come up with a appropriate algorithm to make something like this, where you want to seamlessly stitch all those images and then make a mosaic of things. Yeah, this you would hardly see. If you see any individual image, not the subsequent, not one after the other, the frames, you could hardly see the object. This is again, of course, a very synthetic, tailor-made, purposefully made example here. So this, you could see the object in it. So this is just to illustrate that there could be situations where a static frame itself will not give you much information, but once you are doing keeping track of things, you could do things, you could find out where the object is lying. Okay, well, then there are other possible applications as well. So shape from motion, there is another application is there, where you figure out what is the height of the object at different things through by looking at how the pixels are moving when you are looking at the object. Okay, dynamic model, so you want to make how they cloud estimation, like cloud motion estimation is another thing, where you want to do a weather forecasting. So there you have videos of that captured, radar based videos or whatever it is. You could do different fancy stuff there if you have that information. Or even how the objects would be moving. You are working on a tracking application. Okay, then also this motion estimation would help you to figure to make an assessment on where the next where it will be moving. Okay, keeping track of things. Okay, and then anomaly detection is another important application people work on. You expect certain trajectories, typical trajectories, and if you see some abnormality there also you would require to do that. Integral part of that would be an important component of that. Again, motion estimation in itself might not be the end goal, but you would see it being required for many high level applications. Okay, and then even there is a jerky motion in your camera movement that also in fact can be compensated once you keep track of the motion estimation through certain appropriate models. Okay, so then we come to what are all the different ways you could estimate this motion. One is feature based methods. So this is what we have already covered. So what we mean here is you won't be capturing the motion or the entire image, but you rather pick those key points, okay, which you could reliably keep track of. And then you estimate how much displacement they have undergone to the subsequent frame, and through the whole thing you would estimate the how much motion is there. That's feature based method. So where you would whatever we have discussed in the earlier classes, starting from key point detection, key point description, then key point matching, followed by parametric estimation, whichever we have studied there. All those things put together will help us to do it. But in this, what we would be in particularly the optical flow falls into the second category. It's not at some key pixels. It's in fact at every pixel we want to keep track of this thing. Okay, and that's why since you are keeping track of it at every pixel, these are called as dense models. These are sensitive to appearance variations. If for example, earlier you might miss certain regions where there is no key point, but this is not the case here. But again, it has its own advantages and disadvantages. For example, when the motion is small, this will be very helpful because you will be looking at in the surroundings of that pixel to find out a correspondence. Okay, so if the motion is too large, the way you model your optical flow method, it becomes difficult unless you have the right model. On the contrary, motion estimation as such doesn't have any strict stringent constraints on how far it should not move or anything like that. So even tens of pixels, it will be able to comfortably capture that motion. Okay, another example here. So that white region should, for example, if you look at this region, oh, oops, okay, I thought pen would work, but it should work actually. Let me check it out. Yeah, okay. So if you look at this region, okay, this all has uniform region. So optical flow, now that you all have gone through it, you will know that you will be looking at a pixel which has the same intensity. You are looking at one point, you will look at in the next image for this particular point, for example, the same point you take here and you look in its surroundings for the best match. But if the whole region is having the same intensity, it cannot figure out where it has to move. So that would eventually could give you the same point. So that's why you would see here, for example, there is let me go to the pen mode again. Okay, this region, if you look at it, it doesn't show you any motion as such, although there is a motion on that. Okay. Another thing that you could observe is those points which are closer to you here, they appear to have a large motion here. Okay. And which are farther here, right? They have a smaller motion here. Okay. So this is obvious because it's far from it. So the number of pixels that are representing that motion here, this again comes from the depth. You could also see somebody which is, it's like looking at the motion of with respect to the moon. You are moving and looking at it, how far it looks like. Very similar to it. Of course, that's a another extreme end where the distance is very high. But even when the distance is small, also relatively small, that in that proportion you will see the velocity fields changing. Okay. So this is what the, yeah, that's all for the introduction to motion. Okay, I'll stop the sharing here and let me check if you have any questions so far. Yeah, do you have any questions for this part? Is it clear to everyone? There are no questions at all?
Sir, I have one question.
Yes, good. Yeah, tell me.
Sir, in the optical flow method, like in the dense method, actually, we are
Ah.
not interested with motion of all the points, or just we are tracking a certain region. Is
Ah.
it?
So that's the question, right? You're asking whether we are interested in motion of all pixels or is it just some pixels? That's the question, correct?
Yes, sir.
Yeah, it's a good point. It depends on the application, in fact. What is it that you are trying to do is what dictates what kind of things you would expect there. So for example, assume that let's take some application and then see how does it, whether what will be imparted. So for example, you have you have two cameras set up, or and then you from that you want to figure out how much speed a vehicle is going now. Okay. So for that, once you detect that this is the object, assume that somehow you got the segmentation of that object as well. And then what you would be interested in is to just one representative velocity value for the whole object is good enough for you. But such many objects could be there, but for each object you want one representative value. So depending on, so this is for example an application where do you want one single value or do you want multiple values? It lies somewhere in between for this example, correct? So you want, you for the whole region of that car you want a single value of displacement there, right? On the other hand, the toy example which we have seen where the dice is moving on a for example on a platform is moving, and that there is on top of it there is a dice. Probably in that application you don't really you might be interested to just know one value for this entire thing. So this is governed, or this is dictated by your application. That's what I would say.
Okay, sir.
Yeah. Yeah, for example, even in if you take uh, registration, like for example, that's where probably take a medical imaging application. There also you do this optical flow based registration is also done, where you find out the mapping between them. So in that case, you are morphing one image to the other. So that is in fact the application where you wanted every pixel. You are interested in that dense. You are interested in the dense displacement field. So that's one extreme, another which is there, and the other extreme where you want at every pixel how is it getting morphed to. That's what you wanted. So basically, what is the nature of the object that you have in it? So if for example you are doing some stretching, okay, here so you just want to in which position you are in and which position you are in the next frame, you want to find it out. Okay, so for example in that case you could get the displacement fields. So this is let's say an Xbox, and these kinds of games are there before which you are playing that. So in that case, one representative value for the whole one module of your like one join to the next part, you do a wireframe model there, and for the whole that module, one single representative field is good enough. So essentially there you cluster them into meaningful groups, and then assigning one value to that particular cluster could be good enough depending on the application. Any other question before we move on to introduction to optical flow? Yes, Vaishnavi.
Sir, in that feature-based methods, it is like we are selecting some points and calculating the motion with that,
Right.
and we'll be giving that values to all the pixels, or it is like finding the global motion, or
Right,
can we
right.
do it
No,
for?
that again is very tricky. See, that simple thing which we mentioned is actually trivial, is making things too simple. So there could be applications where that could work out. Not in all situations it will work out, because uh, assume that you already got an object, okay, and on that you are assigning. So you got the segmentations for object in the first frame as well as in the second frame, and you know for sure that this is undergoing some affine transformation. Assume that this object is undergoing some affine transformation. So in that case, getting extracting certain key points and then obtaining them and assigning it, interpolating it through the entire object would make sense, but it doesn't make sense for all the cases.
Okay, sir. That means if I mean, all the pixels are moving in same direction, then it will work.
Right,
Otherwise, it
correct.
won't work.
Correct. And also
Okay.
what you could do is, for example, any tracking application, you might first would like to get a bounding box around that object. And within that bounding box, you might be extracting certain features, and you will do the same in the other subsequent frame also. Then you will try to map the both. So those kind of specific scenarios, it could work.
Okay, sir.
Yeah, that's a good point. Any other question? Okay, if there are no questions, then we will move on to the next presentation, introduction to optical flow. Again, let me share the screen. We are done with the 18th lecture. 19th will go here. Okay. Yeah, this is just a well, so optical flow, what it does is it looks, for example, brightness. Instead of brightness, to make things easy to comprehend and to begin with, we considered here the colors. So you could see that the one whichever is here is looking around. So you will start, so this corresponding pixel might be here. You will look at in its surroundings and see where this color is mapping, for example. Okay, that would give you that this is your field. So similarly, you consider for this pixel, you want to find out the motion where it has moved. You take the pixel here, and then again you take a neighboring pixels there and look at where that color is mapping. So for that, it has been here, so that would give you the mapping. So similarly, another might be here, the same color when you look in the neighborhood. This is the displacement field you are getting. Okay. Similarly, the one here would give you the displacement field here. So we displayed them here in terms of color, but the same thing applies to even having the intensities. Okay, and so the key assumption here is the intensities of the objects are remaining same when you move from one frame to the subsequent frame. So that's why we are calling it as, this is the constraint we are posing. That's brightness constancy constraint. What it is telling you is there is a value of u and v, which you could find out that this exactly the same intensity at x plus u and y plus v in the subsequent frame, t plus 1th frame. Okay, that's what you are doing here. And then we derived this equation also on the notebook. We did that out. So let me, if you want, we could quickly go there. Let me end this show, discard the changes we made, come here to the optical flow, right? So this is the one, I x y t equal to I of x plus u, y plus v, and t plus 1. We assume that the motion is is of order of few pixels around that only. Otherwise, the linearity constraint for the Taylor series expansion gets violated. And then, so that is how you expand this term of x plus u, y plus v, and t plus 1. Okay, this is fairly simple. And then you end up with the di by dx times u plus di by dy times v is equal to minus di by dt. So the same thing we have also have written in a matrix form as well as a vector inner product form, because that would be helpful for us to make an interpretation on. Our variables here are how many u and v are the variables to be computed. You have one equation and two variables. That's the scenario here. So this we are doing it every pixel. So here you could see ix, iy multiplied with u and v is as good as taking inner product between gradient of I and uv, giving you minus it. Okay, and you already know which are the values that we know. It is nothing but x yt plus 1 minus x yt, that you know. Gradient of I at that pixel you know, and you need to find out u and v. So the left hand side is giving you the projection of u and v on the gradient of I. You could see here all those other vectors of u and v plotted will give you the same projection on gradient of I. In other words, you could correctly get, so basically to the image the gradient is perpendicular to it, and you will get correctly only the component that is in the direction of gradient. In other words, whichever is there perpendicular to the, you can get only the perpendicular component to the edge correctly, and the rest it could take multiple values. So this is exactly similar to, or in fact same as what we have seen earlier as the aperture problem. Where did we see this aperture problem earlier? Did we study aperture problem earlier in our course?
Yes, sir.
Yeah, where did we study?
Sir, key point tracking.
Right. Key point. That's right. That's right.
Detection.
Harris corner
Detection and tracking. Yes.
Then mapping also, it could go to, so suppose if there is an edge, if you take across an edge but not at a corner, if you have taken it, it could get mapped to any of the various points along the edge. If the, in the other direction, if it is uniform, there is no gradient in the other direction, you could end up with getting mapped to multiple points. So you have in fact a similar problem here. That's an aperture problem, right? This is an example where if you look at the whole object, you could tell each point where it has gone through. But the moment, so you could see here, for example, horizontal move and this move. Okay, but here you could only get horizontal, or in other words, that which is perpendicular to that edge is what you could get. So what, when the moment you are looking in just in neighborhood, it's like the first two images like this and the second is this. This is all that you are looking at. So it could give you multiple interpretations or even sometimes wrong interpretation. This is one example. If you look at just this and this, okay, so this is the first image, this is the second image. All you could track is which is there in the perpendicular to the edge. You could say it has moved like this, but in fact the movement could be, if you notice here, it could be diagonally the movement is there. In other words, not in just, if you consider this as an x, not in x, not only in x but also in y is there, but that you would never be able to see when you are only looking at a local region. So this is the aperture problem. This component which is perpendicular to the edge you could compute, but actual moment in order to get plus this vector of it in the vertical component also, that would give you the exact motion there. Right, this is another example where if you are just looking at the colors there, it looks like if it is moving in the upward direction. Okay, so apparent motion is in the upward direction, but true motion is in the horizontal direction, because the way you are like looking at it is based on those gradients of those colors in the local direction, where that gradient is also, the edge is in this direction, so you are getting this component correct but not the other thing. And so this tells us that optical flow is not all the time motion flow, because the motion could be, if you talk in terms of the edge, parallel to the edge there will be a component, and perpendicular to the edge there will be component, and those put together gives you the motion. But here what you could in fact are getting here is only one of those components, and other it could take multiple values. There is an ambiguity there. So that's why you are saying here optical flow is not equal to motion flow. Yeah, that's all for the second presentation. Any questions here? I'll go back again to the Zoom. Zoom, where is it? This is that. Okay, and let me stop this for some time here again. Yeah. Any questions on what we discussed?
Sir, can you repeat what conclusion did you bring from aperture problem?
Okay, so what we are saying there is when there is an all you could get here with this optical flow. See, in optical flow, if you are just simply looking at the brightness constancy constraint, then what you are looking at is you have gradient information there. The gradient's inner product with u and v is what you are computing there, and that equal to minus delta of t. So whichever component is there perpendicular to your edge, that's what you would get exactly. But whichever component parallel to your edge is there, that you won't be able to say it for sure. That's the conclusion here. So there are multiple solutions. See, to look at it in terms of the equation, there are two unknowns and one equation to be satisfied. You have multiple solutions, correct? The same next what we did is we are trying to make the same interpretation now from the geometrical point of view. What is exactly having inner product of gradient of I with uv and making that equal to minus I. That's the second way we interpreted things. And then we could see that anything you are getting the parallel component to the gradient of I, correct, but the other orthogonal component could have any value, and any different values would result you in the same value of gradient of I inner product with u comma v. That's the conclusion there. Is that clear, Aravind?
Yes, sir.
Okay, good. Any other question here?
Sir,
Yes.
sir, you have said that there is a constraint on brightness, no, sir.
Right, correct.
What if, 2 point in motion estimation, you have given 4 colors. What if 2 colors are matching for different locations?
Yeah, that is, in other words, that is exactly equivalent to having multiple solutions. There is that's why you have multiple solutions there. You see again, if you have already gone through the next video lecture also, you would say there that having a different gradients is also very important, because then only you will be able to resolve what's the exactly the other component also. So you will end up with ambiguous solutions. See, that's exactly the same thing when there is a dice is moving on a rolling platform. Okay, if you see on the rolling platform, it was whole white. That means each pixel you have multiple possible correspondences. So it's up to you on how you consider, but there is nevertheless, whatever you consider as your solution, there is always an ambiguity there. Any other question here?
Sir, in the
Yeah, Ketan, yes.
Example with spinning this this spinning cylinder, sir.
The spinning example, huh?
Yes, sir.
Okay, that's a tricky
Spinning cylinder example.
I wish nobody would ask a question on that, but
how is the apparent motion?
Yeah, that's a tricky.
Upward there.
I was hoping nobody will ask a question there. It's not as simple as that actually.
Okay.
So it has many other effects. There were in fact PhD thesis on that work. So that is not as trivial as I mentioned there. In fact, it's more trivial. It's more complex than that. So don't read too much into that example. If on the surface you feel satisfied with an example, go ahead, but don't dig there too much deep with only looking from the optical flow point of view alone.
Okay, so it's beyond our scope.
Fully,
But
when you see on one side a vertical motion, but actual motion is a horizontal, where both of them are perpendicular, right?
yes.
Yeah, that's not a trivial thing. Actually, it has many other effects also coming into play there.
Okay.
That's a good point. Anyone else have any questions? Okay, so let me check once the poll again. 30 of 43 have participated there, so around 57% of students have are gone through. Yeah, there are around 40% of students who have not gone through the last lecture. Okay, so anyways, you please go through it. But anyway, now I will quickly go through it. But later, make sure you go through it, and even if you don't get any doubts or clarification doubts now, but later while you are going through it, if you get any questions, do not hesitate to drop me an email, or even if it can be discussed quickly in the next class also, I'll be fine with that. We could discuss that, but make sure you go through it. Don't leave it just because we are done with the class on it. I'm fine discussing on that next class also, but quickly on that. But from the next class onwards, to the extent possible, myself also, I'll try to share that at least one day in advance, and you also please make sure to go through those videos before the class. Okay, let's go through. Let me again share the screen, go through the last presentation for today. The smooth optical flow, and yeah, those are the other two were very basic. This is where we had some things, more things to discuss. Right. So we have seen, in fact, there is one equation, two variables are the best way to solve, as it could have multiple solutions. So you'll never just solve it using brightness constancy constraint. See, in practice, you could always assume that just only one pixel will not be moving, and each pixel will be moving in random directions. Is a very, very unrealistic assumption. So in addition, what additional assumption that you would make here is that all pixels in a region would be moving coherently in one direction. That's what the assumption that's made here. So with that assumption, okay, so this again was a recap of things, one equation, two variables thing. Then we come to Horn and Schunk. Okay, so again here, let me go through the notes there. Right. So what Horn and Schunk does is that see nowhere you will not try to make any of those terms as such to be zero at every pixel, but rather now you take on one side, you look for what is the best match for it in terms of intensity, and on the other side you look at where your neighbors are moving. So you give a weightage for both, and this weighted sum of the values is what you try to minimize rather than simply minimizing one of them. Okay. So this one, on one side, the first thing you have this brightness constancy constraint is there, EC is there. And then comes the smoothness constraint, where the smoothness term is, what it has is ux square plus uy square plus vx square plus vy square. Okay. You know what is u and v. At a given pixel, u is the motion that you have in the x direction, v is the motion that you have in the y direction. What the smoothness term is telling you is, first take the motion in the x direction. Okay. For that, you look at the horizontal neighbor, how much is it having in the horizontal direction, and similarly this horizontal motion, how much your neighbor on your top floor is having. Okay. You also look at how much horizontal motion the person who is your next neighbor in the same floor is having. That's what the first ux and uy would take care. And vx va is the vertical component in your horizon, in your neighbor next door to you, and the other one is who is there on the top floor. That's what vx and vy is looking. So this has to be very clear for you, because otherwise initially it would be confusing. What is ux, uy, vx, vi? Ux is horizontal component for at x plus 1 y pixel compared to the current pixel xy. Uy is the horizontal component at xy plus 1 and the current one. The same thing now for vertical component would give you Vx and Vy. See, these values could be negative also. So that's why, but what you are interested more is in the absolute values. So that's why you will take square of them. Similarly, the same logic holds for the brightness constancy constraint also. Let it slightly diverge from the becoming 0, but you are interested in the absolutely value. So that's why you have a square there. EC plus, we have written lambda plus ES. Yeah, in some textbooks, they would rather have this lambda with EC, but it doesn't really matter. It just what's the lambda value it would modify. But essentially, what you have is these two terms which are weighted by a factor lambda. So that's what this is what has been proposed by Horn and Shun sometime around 1980s. Okay, in artificial intelligence, this is from the work from MIT Artificial Intelligence Lab. Okay, and then I think this is in the next year by Locus and Canade. Okay, this pronunciation I always found it confusing. So Locus and Canade. So now you could already notice that in the earlier case, for this term to become 0, the smoothness, the whole for that, if you put a lambda, for example, very high, that means you are completely relying on the smoothness term. So that means as long as this so all pixels are having the same motion in horizontal as well as vertical, that is when your ES would become 0. So again, there could be multiple objects moving in the scene depending on the application you are looking at. So posing a global constraint on smoothness is harsh. So that's what is relaxed in Locus and Canade. What it does is, well, let's pose this smoothness constraint in the neighborhood of a given pixel. All we say is all the neighborhood behaves in the similar way. So you, for example, could take a 5x5 window around the pixel. So there are 25 pixels. For all these 25 pixels, you write the brightness constancy constraint equation and assume, so you have still, since you are assuming that all of them would move with the same displacement or same U and V values. So there are only two variables here, but 25 equations. So yeah, just before this lecture, we had one equation and two variables. Now we have 25 equations and two variables. Not a bad thing to be in. Okay. So this again, we solved it while you are doing the image transformations. We had the same problem there. So this is exactly equivalent to then multiplying it with this is AX equal to B or AD equal to B. I used to be consistent with other places. AD equal to B. So you multiply with A transpose A. Okay, then you take inverse of it, you multiply with A transpose B. That would give you the E value. So this is exactly equivalent to minimizing the norm of AD minus B L2 norm, or you could also this is a least square fit problem. Exactly, if you are doing the least square fit and you are writing for these points in the doing it in terms of the matrix manipulation, this would be operations. This would be exactly the same thing. So further, what we had looked at here is what exactly is this A transpose A. Okay, there are Ix, Iy are there to distinguish it for each point. Here we are writing Ix for point P1 with multiplied with U plus Iy at P1 multiplied with V should give you minus of I subscript T at P1. So this way we had written here. And then A transpose A, you write take transpose of it, you multiply it, and then you will be ending up with this long expressions here. Ix square at P1, Ix square plus P2 plus so on. So it's all summation of Ix square values at all points. Summation of Ix multiplied with Iy at for each point, and then summing up over all points. The same thing as the second row first column, and the second row second column will be sum of the first order derivative of Iy, okay, with respect to y at each point, squaring it and summing it up over all the points. So this is what A transpose A is. So this should already ring a bell in your mind that you have seen this expression earlier, right? Where did you see it?
Harris corner detection.
Right, Harris corner detection, the second order movement. That is where we have seen it for this to have. So what was there? You had two eigen. You are there also looking at. So A transpose A for this inverse should exist here. That's the whole thing. Because from here, if I have to write some more here, okay, let me write with this. Okay, and after that, what you would do in order to get the D value, you do A transpose A whole inverse, and that is what you would multiply with A transpose B. This is what would give you D, correct? So that means inverse should be a well behaved and not an ill behaved matrix. For that to happen, it should have distinct, that we again interpret in terms of the eigenvalues of this 2 by 2 matrix. For that to have distinct eigenvalues, what should happen? So this is exactly very interestingly, when you look at in terms of eigenvalues, these are identical problems. Okay, this interpretation is it requires a bit of effort to get it, but this is a very nice interpretation I found in geometrical interpretation of when this is well behaved and when you have a good inverse for it. Okay, not mathematically behaving inverse. So what would happen here is, look at here, for example, this pink or red, I don't know. Okay, this color, but or maroon, I think, right? Yeah, this maroon color, if you look at, is the edge at a 1 pixel, and then this gradient of I, in that you will have, so that the locus of points at any pixel would give you a line. That's what we have already seen in that previous video lecture, right? So only the component which is parallel to gradient of I, you know, but then you have a locus of points. All those locus of points is making you one line. Now, among those neighborhood pixels that you consider, if at any of those pixels, if the gradient is varying, it is having a different gradient, then you will have line with a different slope here, all possible things. See, again, this line would be perpendicular to gradient of I. That might not be so apparent from the way I have drawn here, but if you have carefully draw it, you will see that this is exactly perpendicular. The locus of points for a given pixel that it could take will form a line which is parallel to the edge, or in other words, that should be parallel to, perpendicular to the gradient. So if you have a different gradients, then there is an intersection of these lines, and of course other pixels around it are having different, some more gradients. All are expected to ideally intersect at a single point. If not, mean square error, that's what would happen. And that's why if you have a, again, now you think of having a very smooth region, okay, very uniform region of, just like you had earlier example, all white 255, then every point would contribute to a single locus of points. Okay, that means it's as good as looking at one pixel and then still you don't have a very good solution there, right? So this is why you take a neighboring pixels, exactly the Harris-Karner detected the desirable, what are the desirable properties for getting a good corner point are indeed applicable to have a good inverse here. In other words, to have a good solution or the correct right solution for optical flow also. Okay, with that, I again go back to this presentation now.
Sir, I have a doubt.
Yes, sir. Yeah.
What does this intersection signify?
Yeah, that intersection, see, one is telling you these are all possible solutions. This is more like what you got in the Huff transform. See, one is telling you these are all possible solutions, one line, it's the locus of points for that particular pixel to satisfy the equation. Another one is telling you that these are all possible solutions. The intersection point would satisfy both, so that's the ideal solution in an ideal condition.
So, sir, in an ideal condition, this point should actually map to that intersection.
Correct, correct. See, so for example, here itself, this is your gradient, okay? And then any solution can be taken across this line here. Now, similarly, for some other point, this is all, it could take any point on this line here. So this would be the solution now. The intersection would satisfy both, that giving you the solution.
Okay, sir.
Yeah, good. Any other question here?
Sir, it means that u comma v is the only point for that entire entire 5x5 map.
Yes, that is how we started. Basically, that's u and v is a single solution for all those neighboring pixels is where we started. But again, I am telling you here, that is how we are pretending it. This will not necessarily be the it could be or it might not be the case, because you do the same thing for the next pixel also. This is what you do for finding out u and v for a given pixel. Okay.
Okay.
The moment you move, depending on the other pixels that is involving there, this might vary. So at the end, those pixels might, but if it is very similar in terms of the statistics and other things, if it is very in terms of the gradient, even after your sliding window, if it is same, you will end up with this solution, but nothing, it is not guaranteed that it will have the same solution.
Okay, fine. So finally, like,
yes.
After intersection of all those points, sir, like what I mean to say is like the locus meeting point,
right,
that will show the proper u comma v.
Exactly.
Okay, fine.
What could happen is there could be one more line. All the three lines might not be exactly intersecting at one point. So then if you look at it, it will be more like finding out a very that point which gives you minimum error with respect to all these points.
Okay, sir.
Yeah, good.
So, like, what is the issue with the first one, the horn and shank problem, which said it is too harsh, the global solutions?
Right.
What's the issue with it?
Yeah, in the global solution, you are making in an image, assuming that my neighbors around that pixel, all some part of the neighbors having the same displacement, versus everyone in this image should have the same displacement. That's what the first condition is. Second one is that, well, not every pixel in the image should have the same displacement, but if you are having a displacement of u and v, we prefer having your neighbors also have the same.
Okay, fine.
Yeah, good. Any other questions? Yes.
Sir, in the horn and chunk, how did you come up with the EC equation, sir?
Okay. So this was okay. By the way, there was a mistake here. This should be this should be plus here, by the way.
Thank you, sir.
After writing it, that was exactly the same optical flow equation in the previous video that we did it. Okay, see, at every pixel, this is what we derived from Taylor series expansion and other things, right? Brightness constancy constant. That's exactly what we discussed here. Okay, this was the equation. All we are doing, taking it to 0. What we are doing it, since this is not the only constraint we are posing, multiple constraint with some weight is what we are posing. So you are bringing IT to the other side, taking square of it, summing it over all pixels. That is part of your energy term.
Okay, sir. Thank you, sir.
Yeah, that was a mistake actually. That should be plus. Okay.
So what is the difference between UX and VX over here?
Right. UX is, this is actually tricky if you don't pay attention here. See, U is horizontal components only. Okay. U is displacement in the X direction. V is displacement in the Y directions. UX is looking how the display, now the subscript now for X and U and V is telling you whether you are looking in the horizontal direction or in the vertical direction for these displacements.
Okay, sir.
Is that clear? This is actually, if you don't pay attention, it could be confusing. So because there is a U is in the X direction movement, UY is again derivative in the Y direction. That's how it sounds like here. It is true, but what you are looking at is UY is looking at your horizontal displacements of yours with a pixel which is there, which is your vertical neighbor essentially. There also, but you are looking at its horizontal component.
Okay, and so what is VX doing then?
Yeah, VX is looking at the vertical components of your pixel at XY and your right neighbor of it. So VX is the vertical component.
UY and VY.
UY, see, UX is looking at the horizontal component of displacement, okay, with respect to your right side neighbor. VX is looking at vertical components of the displacement with respect to your right side neighbor. Uy is looking at horizontal components of your displacements with respect to your vertical neighbor. So this is this, if you could see there. And then Vy is looking at the vertical components of it with respect to your vertical neighbor. Is that clear?
Yes, sir.
Okay, good. Yeah, this you just draw it out. What I would suggest everyone is you could in fact take some values for ux, uy at each pixel, and then try to solve and see these values also. That would give you that will ensure you that you understood it correctly. Otherwise, it appears you understood it, but yeah, this is a slightly tricky thing. It will take a while to get it correctly. Okay.
Sir,
Yes.
here you have mentioned E subscript as minimum of U comma V. What does it mean?
Well, what is you find out now U and V values that would result in minimization of this energy term. You do know minimization. See, what are the variables that you are going to compute here at the end is at the pixel location X and Y, its displacements in U and V is horizontal and vertical displacements. So those are the two parameters that are there to be varied.
Sir, here minimum means the displacement or the minimum error with respect to neighboring pixel.
Minimizing this energy term, finding out U and V such that this energy term will have a minimum value. You find out U and V, those U and V, yeah, I should have written it slightly differently if you want. Let me write it as, okay, this is also again not the perfect notation perhaps, but minimize this with respect to the variables U and V such that this E is minimum.
Sir, so
parameters, those U and V parameters that give you minimum value for this E is what you should take.
Sir, so here we are assuming that that all the pixels of the image are moving with the same U comma V.
No, it is the assuming that all the pixels within that neighborhood are moving, not the whole image. Well, that was the case with Horn and Shank. What you said is correct. You're right with the Horn and Shank, that is correct. But when it comes to Lucas and Canade, you assume that the whole finding out U and V such that, yeah, you're right that we are mentioning it there. So for that, assuming that the whole things are having the same U and V, correct. Just a minute. So can you repeat the question?
So I'm telling, do we assume that all the pixels of the image are moving with the same U and V?
All the pixels are moving with, not really, because see, that is only part of your constraint. That is what ES wants to impose out of these two terms, right? But EC tells you that, let me see, ES wants that everybody should have same U and V. EC wants that let each one go in whatever direction it may, but it should have the same brightness value. That's what EC tells you. And now you.
But we are summing. We are summing over all the pixels, right? So and U and V are variables for.
Correct.
For
correct.
EC and ES both.
Yeah. So if you notice, actually solving up that we have not attempted here. That part we have skipped. So I do not immediately recollect what was given in that text in that paper. But what could happen is this is something you would be solving iteratively. See, to compute ES, you should be knowing the U values at every point. So you would initialize with certain U and the typical procedure. I don't remember I don't know, in fact, how the Horn and Shank did. But what you do is you initialize with certain values. That's more about how you solve this energy equation. So this typical procedure would be you initialize with some values. Okay, if you are there is something called as iterative conditional modes that one could use here. So you initialize with some values and you keep for each pixel changing. You go through each pixel. you keep changing u and v for the rest, keeping constant what is the best u and v here. You do it for all pixels, and then you iteratively repeat this whole process. Okay, there are other methods also, like GraphCats and many other methods are also there. So altogether there is a whole lot of literature on how you solve it. That's not which we are not going through it for Horn and Shank here.
Sir, and why are we trying to minimize E for finding u comma v?
Yes, it's because, see, when will it be minimum? See, for example, if the brightness constancy constraint is satisfied, your EC will be least value. So ideal condition EC is 0, is it not?
Yes, sir.
And similarly, smoothness, if all people are having the same velocity, ES will be minimum. That you want to impose smoothness, so that's minimum value would be ES. You don't want it to shoot up too much, right?
Okay. Okay.
Same is the case with EC also. That's why a combination of those two things you are trying to minimize here.
Okay.
Good. That's a good point.
Sir, so EC is storing the information of the local region, and ES is taking care of the global thing.
I would rather say EC is taking care of, see, in EC also I'm summing up over the all pixels here if you look at this equation.
Sir, so then U and V should be same for all the pixels, right? If you
yeah, I should have written this U and V for all pixels you will be finding out here. It's not just for one pixel. There will be different values of U and V for each pixel, of course. But at the end of your process, you should be getting in one go all different U and V values for each pixel. You will not get a single value here. See, if I had ignored this EC term and had only ES term, I would get the same UV for everything. But now that this EC term is also is dragging you in the other direction, which is trying to, sometimes in the other direction, is to get the same intensity constraint, and it is not worried about whether this all of them are having same UV values or not. There will be some trade-off at which it would stable somewhere in between, it will settle down. This would give you, by the way, UV at each pixel. This once you solve it, you get it for UV at each pixel, because you notice here EC also we are computing, summing it up across for all pixels, right? And ES also you are summing it up for all pixels. So you would get individually U and V values for at every pixel. Yeah, good. All that we have skipped here is how do you solve it is not we have covered here. Let's see if we later in other course, or even maybe let's see sometime if we get an opportunity, we'll see how you solve these kinds of equations.
Sir, and how were the 3 lines coming in that
to final this one?
Yes.
Yeah, I draw 3 lines just to say that you assume that there are 3 gradients. Out of that 5x5 window you have it. Okay, then of course I should be drawing.
So we should have 25 lines, right?
Not,
we should draw
some of those points could have, assume if that region is completely white. Okay, all people, then all guys have the same gradient then. So you will end up with a single line, not even an intersection. So that is exactly ill-behaved, and then there is only one eigenvalue here. So this is a frank one, it would become, and the solution is very ill-behaved. There are multiple solutions are there.
Sir, then how are we getting those 3 lines?
Assuming that assuming that at least there are 3 different gradients in that neighborhood which you are considering in the 5x5 neighborhood. Assume that I should have drawn one more line here, but since my image what I have drawn is already messed up thing, I didn't try drawing it. So assume that there is another locus of points, okay, which should be parallel to there is one more line should come which corresponds to this, actually this yellow line. See, all we are saying is each pixel having, so assume that there are 3 dominant gradients in your 5x5 window. See, all if it is a neighbor, if it is having, for example, a uniform region, there is only one gradient. The gradient is same at all pixels, right? So the locus of points, irrespective of how many points you consider, will be you still have multiple solutions. Just like when will this have a good solution is also equivalent to in Harris corner detector. When will you have a good key point? So whenever there are textural differences around that, or when you have a corner point, that means there are multiple gradients, different gradients there within that, you will get a good point there. So same thing would happen here as well. So yeah, the way I draw the diagram is not good because those lines should be ideally parallel to the edges actually. So the way I plotted was not really correct. So they should be in fact parallel. So you should be drawing it a bit more carefully, then you would see that correctly.
So
Sir, that means
different gradients are good enough to find that point, right? Then
yes, that is right. That is right. So within that neighborhood, at least if you have two good gradients, that's good enough. Because it is already, see, a component which is perpendicular to the edge is already resolved. All that didn't get resolved is which is the parallel component. So for example, all these values are valid things if you take a single point. So if you have anything in a different gradient, that's good enough, in fact.
sir, so we are pretending that u comma v is same for the 5 cross 5 region, but the gradients are not same in that region.
Exactly. So only when within that region it has different see, gradients are coming from a single frame. Okay. The displacements are coming from how they are moving in to the next frame. So here, when within this single frame, when you have your surrounding people are having different colors. Okay, if all you guys sitting in a neighborhood are having different colors of shirts, and then you are moving there in the next image, it's easy to find out. So having different gradients in a way is equivalent to having different intensity values around you. Okay. Then your mapping is more unique.
Sir, that means this u comma v belongs to the corner point detected, no, sir?
No, see, if it is similar to a corner point, you get a very good value there. Let me put it that way. So if you have a lot of textural, so if you have a good intensity distributions around you, okay, around the point of your interest, then you could get a very good solution. So in other words, if that is having a characteristic similar to a corner point, you are more assured of, or you are more guaranteed of a good solution there. Is that clear?
Sir, but we've discussed this having more than one gradient when there is a corner point only, no, sir? That means you're obviously saying that there is a corner point over there, right, no, sir?
It was not only a corner point, it is also when you have textural differences, if you recollect.
Okay, sir.
So you should have a good texture. It is then you would get a good point.
That means this u comma belongs to all the 25 points in the frame, no, sir? No.
Sorry?
The u comma v which we got from the intersection of these three lines.
We pretend we just assign it to that central pixel.
I mean over here, which is the central pixel, sir, among the green, pink, and yellow lines. Sir.
You come back here, you take this central pixel, and for that you find out u and v here. Whatever that central pixel, wherever you might kept it anywhere here from P1 to P25 doesn't matter. But this is the central pixel at which you assign this u and v to this. For example, the next pixel, if you are considering here, that you might be considering like
a
this.
frame centered around that.
Right, correct. If you are moving up, you will lose that column here and you will go to the next. And to that pixel, you would assign this.
Okay, sir. Okay. Thank you, sir.
Yeah, any other questions?
Sir, again, the same thing. Why are we trying to minimize the mean square error here?
What else? What other best thing can we do here? No, see, all I am saying is we are not saying we are minimizing the mean square error, but doing this is equivalent to that is also not a bad thing. So see, what we are saying is all pixels would move the same value. Okay, now we assume that each one is having a slight variation. Then around that pixels, you are taking a minimizing the least square error, and that is what you are assigning to the current pixel, which is not a bad idea. No?
Yes, sir.
Yeah, that's what you are doing. See, that explicitly we are not doing it. So if you carefully go through these details, computing A transpose A, okay, this is equivalent to minimizing that L2 norm of A transpose AD minus B L2 norm, and then that would be equivalent to finding out least square error in the normal sense. That's what it would happen.
Okay.
Yeah, good. So let me then go back to this presentation. What else is there here? Yeah, so this we discussed it now. Smoothness constraint we discussed here. This part we finished. This part we finished. Okay, and then the part we finished. Yeah.
We fourth year.
Yes, you have a class now. Yeah, fourth years have a class now, is it? I could not hear you again.
We have professional ethics class.
Sorry?
We have professional ethics class.
Okay, so 10:30, 11:30, okay, 11:40. Okay, so what I will do is maybe then all we are left with is discussing about the errors in locus and Canada flow. This we will pursue this in the next class. We will finish it off, and then we will go to the next few videos that we have. I'll be posting those things. We keep discussing about that. So we'll stop here. Okay. And then do you think one class is enough for week, as these things are already posted there, video lectures? So where am I? Yeah.
Yes,
so
sir.
Yeah, so in that case we will take the next class again on Thursday. So please, those of you who have the key discussion is over. So those of you guys who are having another class, you can switch over to the other class. You could log off from here. Okay. So the others, if they have any questions from what we discussed so far, you could please ask it. Anyway, the new discussion we will do only later. That other issues with locus and Canada, we will discuss it in the next class. Okay, feel free to sign off from here if you have another class. Yeah, hope the rest are fine with whatever we discussed so far.
In aperture problem, you have said that we cannot detect the motion.
We cannot
detect the motion, whether it is in horizontal or vertical or diagonal.
When we can't able to detect it, when you are trying to find that motion based on brightness constancy constraint alone. Okay, that is why now we are enforcing additional constraints. Through that, you have ended up in the other end. Now you have more equations to be satisfied than the two variables that you have. So you are able to now achieve that. Provided there are some tags attached to it, provided you have some intensity variations within your patch.
So by considering the neighborhood pixels,
that's right.
By using their motion also, we'll consider the whole image motion.
Yes, not whole image. When you come to locus and Canada, it would be the pixels around that neighbor, in the pixels that are there in the neighborhood of that pixel. That's good enough.
The patch which we are taking.
That's right. That's right.
Okay.
Good. Any other questions or suggestions to improve it further?
Sir, can you upload the PDF, sir? 18, 19, and 20, sir.
Sure, I will do it in the
Moodle.
I'll upload those PDFs also in the Moodle. I'll do that. I'll do that today itself.
Sir, can you share the notes as well?
Okay, sure, I'll do that. But bear with those drawings. I'm not sure I'll be able to read them again properly, but I'll do that. I'll share at least whatever is there right now. I'll share it.
Okay, sir.
Yeah, these two things I'll do today itself. But yeah, in case if there are no other questions, comments, or suggestions, we could sign off for today. And again, then see you on Thursday. Okay. Yeah. Then yeah, by any other questions or doubts or comments are there?